It's a pleasure to welcome Senthil back to IAS. Talk about unnecessary quantum critical points in condensed matter and field theory. And he will also be here tomorrow, this afternoon, tomorrow, if you want to talk to him. I'm sure he'll be happy to talk to you. And you will take him to dinner, right? If anybody is interested, send me email by phone. That can be the reservation.
Thank you very much, Nati. It's always a pleasure to come here. Very stimulating, not the kind of physics friends that I normally get to see and interact with. Yeah, so it's my great pleasure to come and talk to you about this topic. So this sort of a condensed matter talk, but sort of a field theory talk, and I'll try to pitch it somewhere so that not everybody is out of their comfort zone all the time. But for that reason, please do stop me, and you probably don't need encouragement for that, but please ask a lot of questions. This is done with my student, Chao Zhang, and a postdoc, Chuyang Song, many conversations with them that helped us formulate the story. So I'm going to get to the main focus of the talk right away and explain the title only towards the end of the talk. I decided to try to do that. So this talk will involve two characters. One is a lattice system. It's quantum antiferromagnets on a lattice, which will be familiar to many of the condensed matter people and some of the non-condensed matter people in the room. And a quantum field theory, which will certainly be familiar to the quantum field theorists in the room and probably also to the condensed matter people. It's massless QED3. And the talk, so QED in 2 + 1 dimensions with massless fermions. And the talk will be about the realization of this field theory in this lattice system and the role that it plays in the phase diagram of the lattice system. So there's the outline. So unfortunately, on many of the things that I'm going to talk about, I'll have to be very brief. It'll be a review of things that different people know, but maybe to bring the entire audience up to speed, give brief reviews of I'll introduce the lattice system, I'll introduce the field theory, I'll talk about why, at least for me, there's a reason to understand the relationship. Then we'll construct the field theory from the lattice, and then talk about the physics of the field theory, and finally show its interpretation as this thing that is called an unnecessary quantum critical point. Okay, so a brief introduction to the lattice system. So the setting is very simple. We have a square lattice. So the lattice is in 2 dimensions. It has all the symmetries for the square lattice. And we populate the lattice at each side. We put a magnetic moment that transforms in the spin half representation of SO3. Okay? So the condensed matter physics, we call this the spin. And we imagine there's some Hamiltonian which has short-range interactions. The simplest thing you can imagine is just nearest neighbor S.S interactions. There may be, I'll allow myself to add other terms which are short-ranged and consistent with all the symmetries I'm going to impose. So I won't really need to specify the Hamiltonian in great detail, but it's the structure of the Hamiltonian that is important. So the symmetries that I'll impose are SO3, spin rotation, like in this Hamiltonian, the lattice space group, and time reversal. Okay, and so we know a great deal about magnets of this kind. The usual fate, if this is the dominant interaction, is that it orders in this pattern. It breaks the SO3 symmetry spontaneously, and you get a magnetically ordered state. It's an antiferromagnet. The spins go up, down, on the 2 sublattices. And the order parameter is transforms in the vector representation of SO3, and it's called the Neel order parameter. Okay, so hopefully this is familiar. Now, in the last 30, 40 years, maybe longer, condensed matter physicists have contemplated other possible phases in such a system. with other interactions. The dot, if you act by playing around with the dot dots, you can obtain other phases. In particular, you can obtain phases where spin rotation symmetry is not spontaneously broken. A simple example is given by this pattern. It's what's called a valence bond solid. And here, each spin finds a partner with which it forms a spin singlet. Spin singlet is this object. So each spin is part of a pair of spins that forms such a singlet. And the singlet bonds arrange themselves in some pattern on the lattice. Right? And I've given an example of a pattern here. So the spin singlet state is invariant under SO3 spin rotation. But this pattern of arrangement of the singlet bonds breaks lattice symmetries. For instance, if I translate this pattern by 1 unit to the right, I get a different pattern. Or I can rotate the pattern by 90 degrees, I get a different pattern. So it breaks lattice symmetries but preserves spin rotation. Okay? And then there are more exotic states called quantum spin liquids that preserve all the symmetries. It's known on general grounds that these must either have topological order, meaning it's described by some non-invertible TQFT, or be gapless, for instance, described by some conformal field theory or some other kind of gapless field theory. So these are possible, and there's a great deal of effort in the field understanding the various possibilities, when they occur, what the universal properties are, and so on and so forth. But the Neel state is by far the one that is common in solids, that occurs all the time. People routinely do experiments where you see the Neel state. Yeah.
Are the other states actually seen in materials?
There is some weak evidence that you might see in some materials as valence bond solid. On the square lattice, there's no material that has been proposed as a candidate for a spin liquid so far. All the searches for quantum spin liquids involve candidates on other lattices, triangular lattice, Kagome, blah, blah, blah. For the square lattice, this seems to be not only the most common in solids, but the only reasonably serious, energetically favorable candidate in a solid state realization. If you play around with interactions in cold atoms or something, who knows what you can get. We do know what you can get, but yeah.
So they've been seen, this quantum spin liquid has been seen with cold atoms, but not.
No. So the quantum spin liquid, it's not, there's candidate materials for it on other lattices.
Okay.
But nothing where I can proudly declare that it's a done deal, And cold atoms, there are state preparation. People can prepare the ground state. Very recently, the people have managed to do things like that, but that's what it is.
I see that you say there it's just by design, so it's.
Yeah, it's by design.
Yeah, the minimum.
I mean, it's interesting in a different axis.
Right.
But if you talk about things given to you from chemistry,
Okay.
we're not in a position to declare that quantum spin liquids clearly exist and here's the material. There are lots of candidates, but nothing is done. So as far as the antiferromagnetic, models of this kind are concerned, I'm mostly going to be talking about this most familiar Neel state, right, in this talk, not the more exotic things that we'll say that something interesting happens in the Neel state. The state that is seen. Okay. So this problem of quantum magnetism on a square lattice is important, not just for its own sake, but it's also important to many other phenomena. The most famous example, the most famous reason why it's important is that it occurs as the parent of these copper-based high temperature simulators, the world's most famous high temperature simulator, right? Still have the world record, at least at ambient pressure for ITC simulant activity. I don't know how many of you have not seen phase diagrams of this kind. Certainly anyone older than a certain age has probably been bored to death by this phase diagram, but the younger people may perhaps not. So there's a very, very famous phase diagram on which there are ordered 10 to the 5 papers this temperature and this is an axis called doping, which means you remove electrical charge from the system. So these materials start their lives off as insulators, which okay, first of all, it's known that the important physics in these systems lives in two-dimensional planes. And each two-dimensional plane, the electrons move on a square lattice, right? So we can forget about all the other complications or all the infinite number of layers, the three-dimensional structure, and focus on two-dimensional structures, 2D square lattices. And it's known that the microscopic Hamiltonian is such that the electrons have very strong repulsion when they occupy the same lattice site. Okay, and the phase diagram is that the parent material, some material like this, starts off as an insulator where there's one electron at each site and the electrons don't move because they run into each other, the strong repulsion. So this is a kind of insulator that's known as a Mott insulator. And this, so the low energy physics, that it's just determined by what the spins are doing, and because the charge doesn't move at all. And the spins form a square lattice spin half antiferromagnetic. They just form the Neel state. And that is very well established. It's known from experiment. It's known from theory and so on. They're totally uncontroversial. And when you remove charge from the system, you find the superconductor, which, so that's what's seen, right? So, so the fact that the square lattice antiferromagnet gives birth to a superconductor when you remove electrical charge from it, that's a big deal, right? And that's one of the premier problems in condensed matter physics. And clearly the square lattice magnet plays a big role in understanding, the eventual understanding of what is going on in this phenomenon of high TC superconductivity. So it's a lot of good motivation to try to understand the square lattice magnet. Okay, so that's my lightning introduction to the lattice system, just to introduce you to the setting. Now let me give a lightning introduction to the quantum field theory. Again, to the field theory, this may be too elementary, but hopefully there are people in the room who don't know the field theory as well as some of the other people in the room. Right? So I'm going to talk about massless QED3. So that theory is defined by having NF massless two-component Dirac fermions in 2+1 dimensions that's coupled to a U1 gauge field. So you can write a Lagrangian of this sort. Size of the fermions, I runs from 1 to NF, and A is my U1 gauge field, is Maxwell action. I'm mainly going to be interested in a particular value of NF equals 4. And this theory can be studied in a, say, in large NF expansion, and it's known that it flows to a conformal field theory in the 1 over NF expansion. And this numerical work, Monte Carlo, this theory doesn't have a sign problem. You can study it with Monte Carlo. And it's known that the evidence is that the CFT exists at least down to NF equals 4. And it's not clear what happens at NF equals 2. It probably doesn't exist. But by NF equals 4, people seem to think that it exists from the numerics. Okay, so I've written down the Lagrangian. Now let's ask about the local operators in this theory. Local operators have to be gauge invariant. So obviously there are things like fermion bilinears like this. There's the field strength, and there are obvious variants. I can make any gauge invariant polynomial for these fermion fields, and that will be a local operator in the theory. So those are the obvious local operators. And then the more interesting class of operators are monopole operators, where I insert 2 pi q flux of the U1 gauge field, where q is an integer. And these monopole operators are accompanied by, in the presence of the massless Dirac fermions, they are accompanied by 0 modes, one for each Dirac fermion flavor. So if I have NF fermions, there are NF fermion 0 modes. And the gauge invariant monopole operator involves spilling half of these 0 modes. So in the case of NF equals 4, I fill 2 out of the 4 0 modes. So that gives me a total of 4 choose 2, namely 6 choices. So there are 6 distinct monopole operators of strength 1, where I have 2 pi flux in the theory. Now, a key point about this set of local operators is that all of them, including the monopoles, are bosons. Right? So the theory only has, I mean, the Lagrangian is written in terms of fermions. The theory, all the gauge invariant observables in the theory are bosons, right? So really you should regard this Lagrangian describing some boson system where the fundamental degrees of, I don't know, maybe not use the word fundamental, where the basic degrees of freedom are bosons, but there is some Lagrangian description which involves fermion fields. The fermions are not gauge invariant, they have nothing to do with physical observables directly. Okay? So there's the first hint that this model could arise in a spin system. Well, in a spin system, of course, there are no local operators that are fermions, right? There are only bosonic degrees of freedom in a spin system, and this model only has bosonic degrees of freedom, so maybe it has a chance of appearing as a low energy theory. Okay? Okay, now let's ask about the global symmetry of I described the lattice system, I told you what the global symmetry was. Now let's look at the field theory that I'm going to talk about, my second actor in this talk. And let me just state the results for NF equals 4. What is the global symmetry of the field theory? There's of course, if it close to CFT, there's the entire conformal symmetry. I'm not going to talk about that. I'm going to talk about the internal symmetry. So namely, there is a topological U1 that's often called a topological symmetry. There's symmetry associated with conservation of the gauge flux. So there's a symmetry, the U1 symmetry. And namely, there's a flavor symmetry, SU4. I can rotate the 4 fermion flavors by some unitary transformation. But this description is somewhat naive. Let me be more precise about some modding out of this U1 topological times SU4. If you look at the monopole operators, the monopole operators are charged under this U1 topology. Right? They insert 2,5 flux, so they change the value of this flux, so they're the charged operators under this U1 topological. Now, the fact that there are these 6 monopoles that come from filling 2 out of 4 fermion zero modes, so what that translates to is that these single strength monopoles transform as a vector under SO6, which is the same as SU4 mod Z2. Right? So these monopole operators, the elementary monopole operators charge 1 under this symmetry and is a vector under this SO6. So the continuous part of the global symmetry is actually SO6 times U1 topological mod Z2. Right? So rotations in the flipping all of these by a minus sign can be compensated by a U1 phase rotation. Right? And then there's discrete symmetries of time reversal, reflection, and charge conjugation. Right? And so this was described long time back, at least going back to this paper perhaps earlier, and in many other papers since. So any questions? So, because the field theory aspects, the field theorists in the room know far too well, probably. But maybe from the non-field theorists. Okay. Now, another piece of information about this field theory that we'll need, it's supposed to be conformal, so do we have some information on the scaling dimension of various operators? So the big expert in the room, Silviu's done a lot of beautiful work on this problem. So as estimates, you can take the 1/n expansion and get estimates for the scaling dimensions. It was done initially in this paper, leading order, and then to the next leading order by Silviu when he was still at MIT. It's a tour de force calculation, beautiful calculation. I used to joke that it is a calculation no one else can do, Silviu can do it. Monte Carlo calculations, particularly from Karthik and Narayan in the last few years, and some input from Bootstrap, again from Silviu and Shai Chester. So what have we learned? Right? So the single strength monopoles have a scaling dimension of close to 1 from both the 1/n expansion and from Monte Carlo. Right? So if these are allowed in the theory, these are certainly relevant. Right? And they'll destabilize the CFT. The double strength monopoles, the 1/nf expansion extrapolated to NF equals 4 gives a scaling dimension of 2.5, while there's a very recent Monte Carlo paper that estimates a scaling dimension of 3.7. So one of them says it's going to be relevant, the other says it's going to be irrelevant, and there's a window. Okay? And my understanding is that Bootstrap barely allows for this possibility, but it's at the border of what may be allowed.
Barely allows which possibility.
The numerical possibility.
So Bootstrap figure is smaller than this.
Bootstrap can give you the range that Bootstrap gives, includes this, but goes to smaller values. That includes the 1 over NF answer as well. So I don't really know, I guess we don't really know what the scaling dimension of the double strength monopole is. But, I'm going to be optimistic and just assume that the Monte Carlo is closer to the truth than the extrapolation of 1 over n. And that this double monopole may have a scaling dimension bigger than 3. That's an assumption that I'm going to make to see where we get. Okay. And of course, if in the future it becomes clear that this assumption is not true, then we'll have to change the story. Okay. Now, for fermion bilinears, as per the 1 over NF expansion, the chiral mass, psi bar psi, has a scaling dimension that's bigger than 2, and the flavor mass is a scaling dimension that's smaller than 2. And both of these are being calculated by many people, including by Silvio in the last few years. Okay? So that's the kind of information that we have. Various estimates based on various approximate calculations. So the most dangerous operator is the single strength monopole. If it's allowed, then you destabilize the conformal fixed point completely. Okay, so that's the review of the lattice and the field theory that I'm interested in for this talk. Now, let me try to give some motivations for why I want to search for a relationship between these two. Okay. So we'll take inspiration from experiment. Okay. So I don't want to flood you with experimental facts, but there's one fact that is pertinent. So I said that the square lattice spin half antiferromagnet is the parent state from which, when you remove charge, you get the superconductor. Now, the other thing that's completely uncontroversial in the field is that the superconductor is what's known as the dx squared minus y squared superconductor. That refers to the internal pairing, the internal wave function of a Cooper pair, the orbital structure of the Cooper pair wave function. And or equivalently, you can talk about it in terms of the expectation value of the Cooper pair operator. And in K-space, it has the structure where it's cos kx minus cos ky. So this changes sign under a 90-degree rotation. Right? So in BCS theory, the standard description of most superconductors, such a superconducting order parameter will lead to the vanishing of the superconducting energy gap at 4 points of the Fermi surface. Right? So this function vanishes when either kx equals ky or kx equals minus ky. So there are lines where the superconducting order parameter vanishes. Your Fermi surface intersects those lines, then you leave gapless points on the Fermi surface at those 4 points. So the low energy theory of such a superconductor, ultra low energies, where you forget about everything else, will involve these gapless quasiparticles where this function vanishes, and then these quasiparticles will have Dirac dispersion. Right? So you have four massless Dirac fermions at low energies inside the superconductor, and this is routinely seen in experiments for nearly 30 years now. Right? So the basic question in the field: how does this Mott insulator, which has no charge but the spins form a Neel magnet, how does it evolve into not just any superconductor, but a superconductor which has gapless Dirac fermions? Right? So this is one of the most basic questions in this entire field of high-TC superconductor. Now, I'm going to give a couple of slides which may look very much like you entered a strong talk that's deep into condensed matter physics. hopefully you just get a flavor of what I'm trying to say. I'm only attempting to give a flavor of the reasoning anyway. This is just motivation, right? So how do we describe any superconductor, right? We can describe it in many ways, but let's follow BCS, the original description. They used a wave function, this kind of wave function. This is the way, for usual BCS superconductor, this is the wave function. And the d waveness is fed into the behavior of these coefficients, UK and VK. Right? So that same kind of structure of wave function works for a d wave superconductor as well. So can we expect this superconductor, this wave function, to describe the observed superconductor in these materials? And the answer is no. This does not have very good energy because it fails to account for the strong repulsion between electrons when they occupy the same lattice site. Right? So this superconductor knows nothing about that repulsion, so it'll have very poor energy. This wave function will have very poor energy. So a much better wave function is to just take this, this state and simply project out states where more than one electron sits at the same lattice site. Just remove them. So expand this and say in a configuration of where the electrons sit, and just physically throw out all states in which there's more than one electron sitting at the same lattice site. So you project those states away. So this has been, people have worked with this for decades, and numerically, it's known that this projected wave function captures both the universal aspects of the superconducting state. It retains the structure, the universal aspects of this wave function, but it also captures non-universal microscopic trends in experiments, such as how the superconductivity weakens as you decrease the doping and go towards the insulator. Right? So it's a huge amount of work in the last 30, 35 years, working with wave functions of this type. So the total number of electrons is less than 1 per site. That's where the superconductor occurs. This describes a strongly correlated superconductor, not just a BCS superconductor, but a strongly correlated version of the BCS superconductor. So the natural question to ask is what happens to this kind of wave function as you increase the total number of electrons so that it's equal to 1 per site, because that's the limit at which in the experiments you don't have a superconductor, instead you have an insulator, right? And where you have long-range antiferromagnetism, right? So given the success of this wave function, you want to understand what happens to it when there's no dopants in the system. Yeah.
Was D-wave superconductivity put in by hand? And you're using these?
Yeah, that's right. Absolutely. Yeah. Okay, so the question we want to ask is, there is this wave function that describes the superconductor and gets things reasonably correctly in terms of trends in experiments and universal properties. Now, we want to ask, if you take the same wave function and go all the way to x equals 0, then what is the state, right? So the projection with with 1 electron per site, the projection freezes the electron charge completely, right? We have thrown out any sites with 2 electrons, right? Any states where there's 2 electrons per site. The projection ensures that I have exactly 1 electron on each site, and then the charge is no longer a degree of freedom. So anything that's left is the spin. So there's some wave function for an insulating lattice magnet on the square lattice. And again, I'm not putting references because it's far too many to the numerical work. There's 35 years of work in the field. But there's numerics that show that you can measure, say, the spin-spin correlation, and it has a power law in this wave function, right? At 1 electron per site. And then there's no broken symmetry. You don't break spin rotation, you don't break lattice symmetries, and so on and so forth. So we have a wave function, but we want an effective theory that for which this wave function is a caricature, right? So you might guess that the naive guess, maybe it's the same low energy theory as the mean field D-wave superconductor, namely a state with 4 massless Dirac fermions. But that naive guess is clearly wrong, because now I have an insulator with no charge at all, right? There's no fermions in this lattice magnet. So this theory has local fermions, but the lattice magnet cannot have any local fermions. So you have to hide the local fermions somehow. And you might guess that you might improve on this guess by saying, okay, let me keep these fermions, but let me hide them from the system by coupling them to a VHP. Right? Meaning to get some theory that looks like QED3. So that's one motivation. Yeah.
Your previous transparency, the fermions were physical, right?
Absolutely, yeah.
So
They were physical here, and they've been seen in experiments.
Right.
But then once I move here, it's a spin system. Fermions cannot be local physical degrees of freedom.
But, well, maybe I'll show us how it works, but it can be hard to have a system without fermions. It has fermions when you slightly perturb it. But perhaps how it works will be clear in your lecture.
Sorry, I didn't hear the first.
Well, you'd be saying that there are no fermions at zero doping,
Right.
but at doping epsilon, there would be fermions.
That's right, yeah.
Maybe we'll see that in the low energy field theory as well.
I won't really address that question, but that has been addressed in the past literature on this topic, but it builds off. I'm going to address the state from which you can get something like that. Right? But this focus is going to be on the state in the magnet, which is such that once you dope it, it can have low energy fermions. Okay, so this might be a guess that perhaps something like QED3 works because it has the Dirac fermions, but it's a theory of bosons, right? So it sort of has the right structure that's needed to both match a purely bosonic theory at zero doping, but then it may have enough in it to give birth to physical fermions once you remove charge and get into the dope state. But that's motivation. And if this didn't make sense, that's all right. We can continue with the rest of the problem. I mean, if it makes sense, so wonderful too. Let me put it this way. This was one of my motivations to consider this problem. All right. So now let me forget about all the inspiration from experiment and just focus on the lattice magnet, right? And ask whether we can construct this QFT directly from the lattice, provide some level of construction. And to put it in quotes because it won't be a derivation, it'll be a construction. I'll distinguish the two. We'll see why. So this construction is actually very old. It again goes back 35 years. And methodology is what's known as partons. So I'll explain what it is for lattice magnets. So we have a spin half degree of freedom at each side of the lattice. Right? What we do is to represent the spin half degree of freedom in terms of two complex fermions or equivalently 4 minor fermions at each side. Right? So we write the spin using the complex fermion notation. We write it this way. And this is a faithful representation of the spin, so long as we impose a constraint that there's exactly one fermion at each lattice site. Right? So this local constraint leads to some gauge structure. So this representation in terms of fermions is a highly redundant representation, and I have to impose a constraint to get rid of the redundance. Right? You can think of the constraint as leading to an SU2 gauge structure. If you wish, there's with 4 minor fermions, there's natural SO4 action, which is, and you're gauging an SU2 subgroup of the SO4, and then what's left behind is the other SU2, right? And so the idea then is that we take whatever spin Hamiltonian we imagine describes microscopic system, we plug in this representation, and then we do we'll get some complicated Hamiltonian in terms of these fermions, and that Hamiltonian will come with a constraint, which is this. And we treat this complicated looking system in a mean field approximation. Right? So this step is uncontrolled, right? But the goal here is not to derive anything, but to provide a path from the UV lattice system to a field here. Right? And we'll see what the utility of that path is. So again, we're not trying to solve any particular microscopic Hamiltonian correctly. Right? We just want to understand what's allowed as in terms of low energy field theories, what's allowed to emerge from lattice systems of this kind. Right? So we'll get a mean field quadratic Hamiltonian in terms of these fermions, and it's quadratic, you can solve it. But the mean field is not the end of the story. You have to do fluctuations beyond the mean field. And the fluctuations will naturally involve some sort of gauge fields because the original representation had a gauge redundancy. And you obtain low energy effective theories of the magnet through a part-on mean field theory plus these fluctuations. So that's again a well-known construction in condensed matter physics, and this reviews which themselves are ancient now, which describe this procedure in some great detail. Okay. So a construction of this kind that led to this QED3 theory actually originated and worked here at Princeton in the 1980s by Affiliation and Marston, who were very much motivated by questions on high temperature superconductivity. So they took this part-on construction, applied it to the square lattice antiferromagnet, and the mean field state that they found is the mean field Hamiltonian of a D-wave BCS superconductor with nearest neighbor hopping and nearest neighbor pairing. Right? The hopping is just nearest neighbor, and the pairing is nearest neighbor. And the pairing is such that it's the strength of the pairing is say plus delta naught on horizontal bonds and minus delta naught on vertical bonds. That gives it its D-wave structure. At a 90-degree rotation, this pairing amplitude changes sign. Okay. So this started this, there's again hundreds of papers since Affleck and Marston doing this. So the low energy theory of the mean field, just like in the standard in the D-wave superconductor, now there are 4 gapless Dirac fermions. But now, in thinking about fluctuations, we have to worry about the residual gauge field interactions that are there beyond the mean field, because there is an approximation to some complicated representation of the spin system, which is highly redundant. Right? So it's known by analyzing this, you can show that this mean field state breaks this U2 gauge structure down to U1. And so we must couple the fermions to a U1 gauge field. Low energy theory beyond mean field is precisely this NF equals 4 QED3. Okay, so that's the lattice construction of the state. It's involves uncontrolled steps. So, but then I don't know the original, I mean, I'm not specifying the original Hamiltonian anyway, right? So, it's what it is, right? But this gives us a path through which we can construct this low energy field theory, starting from the kind of structure that we have in the UV. Okay?
If you think about the scale.
Yeah.
Let's assume that NF equals 4 theory indeed flows to a fixed point.
Yeah.
Then at short distances, you have a Hamiltonian, say this one.
Right.
Are you saying that there is a range of energies below the microscopic scale, but above the fixed point, where there is a description in terms of NF equals 4 QED3? It could still be that you flow directly from this Hamiltonian to the same fixed point that QED3.
Yes.
But you do not go through that.
Yes, that could very well be. I have no control over anything of that sort, and may very well likely depends on the details of my microscopic Hamiltonian, which again,
But
we're
you
not specifying.
demand that if you start from the UV, first you visit in one fixed point, which is a
No.
weakly interrupting fermion. The very statement that you go through NF equals 4 through ED3 assumes that you.
Right, it's a good. The main assumption I want to make, or the main thing that I want to study is the ultimate fixed point of NF equals 4 QED3. Right? And this gives me a route to constructing a continuum Lagrangian which may flow to that fixed point. Right?
It could be that they both flow to the same fixed point that way.
It could be that they both flow to the same fixed point without ever passing through this Lagrangian.
Within the lattice Lagrangian, what's the relation between the QED coupling and the lattice scale? I mean, they're the same order, or you take them to be at different scales?
I mean, in this derivation,
Yeah.
there's only one energy, I mean, it depends on the microscopic Hamiltonian. Right? If I just took my nearest neighbor Hamiltonian, there's only one energy scale in the problem. But I don't want to do that. I want to give myself the freedom to adjust the UV Hamiltonian and see when I can land in this theory. Right? So that's the logic.
I guess that simplest Hamiltonian had this gap state, right?
The simplest Hamiltonian has this Neel order.
Yeah, that's right. So then,
So we'll
we
see.
need to fine tune sometimes to get.
Yeah, we'll see where the entire talk is about where this theory fits into the phase diagram of lattice magnets of this sort. Okay. So some of these answers, some of these questions will be addressed, as we go along. So one of the utilities of this construction, it's not so much to relate energy scales to low energy field theory to UV energy scales, right? Well, I don't even know the UV Hamiltonian, right? But it is to map UV symmetries into the IR, right? So on the lattice, I have a spin model with its global symmetry group, SO3 times time reversal times the space group. In the IR, I have this 2D3 theory, and we've described the symmetry of the IR theory. It's SO6, Pro-Q1 mod Z2, and discrete symmetries. So there must be an embedding, a mapping of the global lattice symmetry group to the IR symmetry group of the field theory. Right? And this information can be read off once we have this part on construction. Right? So that's one of the advantages of having this part, that we can read this information off. So already said this, and now any operator, so the question of what operators am I allowed to add to the CFT generically, right? So any operator that's invariant under the IR image of the UV symmetries should be added to the IR CFT. Right? So there's some local operator that transforms as a singlet under all the UV symmetries, and that's a legal operator that should be added with some unknown coefficient. And generically, I have to perturb the IR CFT with those operators. Right? They may be irrelevant, but that I have to answer that question first. Right? Now, there's no symmetry allowed operator that's relevant. Then the CFT will describe a stable phase of the original UV lattice system. Right? I won't know where in parameter space I'll find that stable phase, but it must exist. Right? If it has exactly one such relevant operator, then it describes the quantum critical point, and I had to tune, but I only had to tune one parameter in the UV to hit that quantum critical point. Again, I won't know which UV parameter. Is it some diagonal interaction, force-spin interaction? That I won't know. But I know that I only had to tune one thing. So if I have more than one relevant operator at some sort of multi-critical point, and then it gets more complicated and less interesting. So we need to know, what are the symmetry allowed operators in this theory, right? And we saw that the dangerous ones are the single strength monopoles. So you have to understand whether any of these single strength monopoles are symmetry allowed. Right? So you can do that analysis based on the spot-on construction. So again, as I said, that's one of the utilities. And we know that there are 6 monopoles and anti-monopoles of single strength. And it turns out there's precisely one that is a singlet under all the UV symmetries. Right? So there's one operator that you should generically add to the low energy CFT. And it's an operator that will generically be present in any UV system that has any chance of flowing to this IR CFT. Yeah.
How is the UV symmetry is SO3, right?
SO3 times space group times
Right. How is it embedded in the?
Yeah, so the SO3 itself is a subgroup of the SO6.
So the one rotates, say the outer 3?
Yeah, exactly. Yeah. And the remaining 3 rotate under lattice symmetries, but they are singlets under SO3. The 6 monopoles, 3 of them rotate under SO3. They form a triplet representation of SO3. The other 3 form a singlet representation of SO3, but they are rotated under lattice symmetries. lattice symmetries will change one to the other and so on. Except for one of them, which is a complete singlet and should generically be added to the IRCFT.
How do you know that this is how you should map the symmetry?
Oh, it was worked out through this part one construction in these papers. So I'm just taking over. I'm not explaining the details, but so the part one construction gives a recipe and, because there's a mapping. Right? So even though energetically it's uncontrolled, it enables us to answer these sorts of kinematic questions in a clean map. Okay. So this means, since I only have to tune one coupling constant, and F equals 4 QED3 describes a quantum critical point in the phase diagram of such magnets. Right? Okay, so now let me describe the physics of this quantum field theory. It's a perturbed conformal field theory, where I perturb it by adding this allowed singlet monopole. Okay? So the natural key questions of, what is this quantum critical point? If it's a quantum critical point, fine, I tune one parameter. What happens on either side of this quantum critical point? What are the phases and so on? And the right framework to address these questions is to, define a quantum field theory as a deformation of this QED3 or the CFT to which QED3 flows, and I deform it by adding a relevant perturbation, which is the only symmetry allowed single strength monopole in the theory. Right?
And what about the fermion bilinears of QED3 or some of those are?
Yeah, so the fermion bilinears, all of them transform under lattice symmetries. Okay. So they can't be added. Otherwise, it would have killed the theory very easily. Right? And that's again very easy to see, and it's been known for a long time. So this is the only relevant operator that you can add. Okay, so let's define the quantum field theory, right? I'm taking a CFT and perturbing it with a relevant operator. That's a quantum field theory. Okay. So we want to understand what this quantum field theory does. Let's again ask about the global symmetry of this quantum field theory of this CFT perturbed by this relevant perturbation. Right? Now let's recall that the monopoles transform as charge 1 under this topological U1 symmetry and as a vector under SO6 in the CFT. Now, lambda term breaks the topological U1 symmetry completely because it's a monopole operator that's charged under this symmetry. So once I add this monopole, that symmetry is gone. And the SO6 is reduced to SO5 because I'm polarized along one direction of SO6. So I only have rotations in the remaining 5 directions. Okay? And I have discrete symmetries of time reversal and reflection. Okay? So these remaining 5 strength 1 monopoles, they form a vector under an SO5 symmetry group. So the theory, this theory has an SO5 symmetry. And you can identify this SO5 vector with lattice operators from the UV. Based on what we know about how the lattice symmetry embeds into the low energy theory. Is there a question?
Well, if you took lambda to be real.
Yes.
You could have had lambda times phi triv plus lambda dagger, lambda bar times phi triv dagger.
Sorry?
You have a sum of 2 operators, not
Right.
an exact one, with a real coefficient.
Right, the coefficient is required to be real because this is the combination that's singlet under or the reflection.
Okay,
Yeah.
all right.
Okay, the square lattice has enough symmetry to prohibit many things, but not everything. Right? So these 5 components, it turns out they're very, very physical. 3 of them are just the Neel order components of the Neel order parameter, which transforms as spin 1 and SO3. And the remaining 2 are this valence bond solid order parameter that I described earlier. It turns out they're just 2 components of the valence bond solid order parameter. They're very physical objects, right? And then we know one other piece of information.
Why would they transform levels of time?
How would they, or when would they?
Why would those?
Oh, because I had 6 monopoles which transform as a vector under SO6. On the lattice, they don't. I have to add further. In the low energy field theory, there is this thing that transforms the vector into SO5. And I asked what lattice operators map to this low energy operators in the low energy field theory. And it's these observables on the lattice that map to these low operators in the low energy field theory. Now, the lattice doesn't have SO5 symmetry. It has much smaller symmetry. Right? But this field theory has higher symmetry than the original lattice model.
So you are saying that there's an additional operator which breaks SO5 to SO3 times SO2?
Yeah, in fact, it's to SO3 times Z4. And some of those anisotropies I will mention in a minute.
But I could read about how you're putting in the U1 gauge symmetry on the lattice. I mean, why didn't have on the lattice also the topological symmetry of the U1?
On the lattice, I just have a spin system.
So you're not adding the U1 gauge fields also on the.
No. On the lattice, I just have a spin
Things
system.
come from.
Everything emerges, all the gauge fields fermion, they all emerge as some Lagrangian description of some low energy CFT. Right? That's just one description of the CFT and yeah. Okay, now this SO5 cross time reversal, it turns out has an tooth anomaly. And you can derive this in many ways. You can derive it from the field theory. The CFT itself, the global symmetry is known to be anomalous. And when you restrict the symmetry of, when you add this relevant perturbation, you decrease the symmetry to this subgroup. And that subgroup inherits a part of the anomaly. And so there is an anomaly. And one can also obtain this, from a different point of view, one could obtain the same field theory by Higgsing a different field theory, which is an SU2 gauge theory with two massless Dirac fermions. That theory has the same global symmetry and the same anomaly. And then you add a Higgs condensate that reduces the SU2 gauge structure to U1. You don't change the global symmetry of the anomaly, you have all of that. Now, from the lattice point of view, it's good that we have this anomaly because it's a reflection of general constraints that we know from the lattice, the kind that Naki has been spending a lot of time thinking about. These are known as Lipschultz lattice type constraints. And we need those kinds of constraints. Those kinds of constraints, they tell us lots of things, but one of the things they tell us is that you don't have a trivial gap state on the square lattice for the spin half magnet. Right? So this field theory, the anomaly of the field theory ensures that the field theory will not flow to a trivial gap state. So these two things match. Now let me describe a part of this anomaly, just of the SO5 part. The time reversal part I can tell you about, but it's a bit more complicated. So imagine you couple in a background SO5 gauge field, let me call it A5, and you study, incidentons associated with pi1 of SO5 being Z2. Right? Well, actually, so for instance, you might want to turn on a background gauge field which has the usual monopole potential times one generator of SO5. And such a background breaks the continuous symmetry from SO5 to SO3 cross SO2. And what this instanton does is to create a vortex in two components of the SO5 vector. It has zero SO2 charge, but you can show very easily that it transforms as a spinor under SO3. Okay? So which means so that's the anomaly of the SO5 symmetry. And you can capture all this, which is maybe a bit long to say, and capture this in more compactly by saying that it's described by an anomaly inflow from a 3+1D bug, which is whose response has what's known as discrete theta term. And I was actually glad to know that Aharoni, Tachikawa, and Nati are all here. I learned about this from a paper that they wrote 10 years back, that there is discrete theta terms. In fact, we use this, their paper quite comprehensively in this work. So this, if you wish, this is the characterization of the SO5 anomaly for those of you who know exactly what this means. Otherwise, you have to understand this. Okay, so this anomaly, yeah.
So, first of all, the SO5, are you saying that the theory that has only SO5 symmetry and nothing else is that anomaly?
Yes.
And what's the input that goes into it?
Oh, it's this QED3 plus this perturbation, right? The single allowed monopole. Or equivalently, you can work with other theories that have the same global symmetry and anomaly like this SU2 gauge theory with two massless fermions.
But then it will not be this, the description of the anomaly will be different.
So it would be exactly the same.
Exactly the
Yeah.
same.
Yeah.
Even if there's no SO5 symmetry.
No, that theory, the SU2 gauge theory that I just described has SO5 symmetry. So the global symmetry is SP4 mod Z2, which is SO5. And that's the same anomaly. And that's how we derive the anomaly in this paper. We're studying the SU2 gauge.
But this anomaly is also there in the SO6 before you broke it by the monopole.
No, there's a different anomaly which reduces to this anomaly after you introduce the monopole. Yeah.
But this anomaly doesn't depend upon the fact that the U1 was gauged.
It doesn't, yeah.
So you could just have three fermions.
Yes.
Par symmetry.
But of course, this is an anomaly in a bosonic system. I don't want to, so I want to gauge those gauge the fermion parity.
For your interpretation, that's what you want.
Exactly.
But there must have been a parent of the anomaly in the theories that did have fermions.
Exactly, yeah, that's exactly right. Eight massless minor fermions will have this anomaly.
Why 8 and not 10? So with SO5 symmetry. Sorry.
Yeah.
They're in the spinner of SO5.
Exactly, that's right, yeah. So then if I gauge the fermion parity, I get a theory with exactly this.
I was confused by something.
Yeah.
So you had the conformal fixed point QD3, you added this monopole operator, so now the theory is blown to gap phase.
We're trying to decide where it's going to flow.
Oh,
We're just looking at the kinematic properties of the theory.
okay, fine, you haven't thought
Yeah,
Have you matched this anomaly with the anomaly of the corresponding spin system?
in the sense that it satisfies the LSM constraints. The LSM constraints are incorporated into the low energy theory as this anomaly. And the time reversal anomaly. You have to include time reversal as well. So there's a very simple physical picture of all this which was understood a long time back. If you take these pictures of the valence bond solid and you create a vortex configuration of those, then you see that the core of the vortex carries an unbalanced spin half moment. So that's the essential physics. Right? And that again comes from the fact that I have spin half at each lattice site, which is the origin of the LSM anomaly.
So that includes also, in the anomaly, it includes also lattice rotation, no?
It includes lattice rotations, everything. Yeah, that's right. And time reversal. So all of that you get. So all of this stuff, you can understand it by just drawing a few pictures of the lattice, and that's how we used to think about it. But now we've learned that for some purposes, it's useful to recast that into precise statements of the continuum field theory. Right? So that's what I'm doing now. Okay, so the anomaly ensures that there's no trivial gap phase, to answer your question. And that's consistent with lattice LSM constraints. But actually, the anomaly tells us something stronger. And we showed this a while back. It tells us that there's no symmetry preserving gap phase, even with topological order. So by now, we know that there's lots of anomalies for which you can have a topologically ordered state that saturates the anomaly. Right? But this is not one of them. Right? And this is an example of a phenomenon that we first saw in studying some topological insulator surfaces, known as symmetry enforced gaplessness. So there's many papers that describe it in the condensed matter literature and also in the field theory literature. So this is an example of a theory where the symmetries and the anomaly alone, if the symmetry is preserved, the theory has to be gapless. Right? So what is the simplest fate of this theory, right? So we can certainly imagine that SO5 is spontaneously broken to SO4, and there's Goldstone modes and so on. And so this symmetry breaking will be described by a nonlinear sigma model, but to match the anomaly, the sigma model needs to have a Witten term at level 1. And so this sigma model together with this Witten term, is what will, is, this has the right anomaly, the SO5 and time reversal anomaly to match the perturbed QED3 theory. So this is a candidate theory that works as a good long distance description what will happen. Right? And the same theory was written down a long time back as a description of the fluctuations of these two order parameters, the Neel and VBS order parameters, based on completely different arguments, right? So we land in the same place, even from these more formal considerations. Yeah.
So originally we discussed two different ways to get to this already, either direction from the lattice or via QED.
Right.
So I understand that if you go via QED3, you might have a larger symmetry.
Right.
But if you go directly from the lattice, you're not going to have the SO5.
Yes, I'm going to talk about that next. That's the same question that Yuji was asking a few minutes back. So we need to, so there's a description of what the perturbed field theory does. And then we have to include other operators that are there in the in any lattice realization, but they're not necessarily there in the low energy theory as presented so far. Now, there are other possibilities you can consider. You can consider that maybe this perturbed CFT flows to some other CFT, right? And in fact, for many years of my life, I was hoping that such a CFT would exist, but I think the latest bootstrap and all kinds of numerical calculations seem to not support the existence of such a CFT. Rather, the evidence is that it's weakly ordered in the longest case. This would have described a putative continuous phase transition between the Neel and VBS orders. In the numerics, it looks as though it's very weakly first order, but definitively first order. And one can also argue, at some level, against the T-broken gap state, but not rigorously. There's some arguments. All right, so now let me finish by talking about the interpretation as this unnecessary quantum critical point. So let's first discuss this at the level of the field theory, and then I'll go back to the lattice system and ask where it lives in the phase diagram of the lattice system, and at that point, bring back the questions you both raised. So in the field theory, the CFT is obtained by tuning this lambda to 0, right? So lambda equals 0 is the quantum critical point, and for any non-zero lambda, I can ask what happens, right? For either sign of lambda, the theory has the same global symmetry and the same anomalies. But the anomaly is a Z2 valued anomaly, right? So it can't depend on the sign of lambda, right? And furthermore, the two signs of lambda are related by an SO6 rotation of the parent CFT, meaning they have the same OG flows, right? For either sign of lambda. So for either sign of lambda, I therefore expect to get the same SO5 broken ground state. Okay, so I have the CFT at lambda equals 0. I perturb it with either sign of lambda. I go to the same state on either side. Right? It's the state where SO5 is broken to SO4. Okay, so this is already the first sign at the field theory level that I have this unusual kind of critical point that's living inside a single phase of matter. Right, the symmetry broken state, as far as the continuum field theory is concerned, I march along it. And I hit the CFT, and I march further, and I go back to the same state that I started, right? In the sense of being smoothly connected. Now let's ask about the consequences for the lattice system. Now I come to your questions. Actually, Ami was also asking the same question. So the orientation of the SO5 order parameter depends on perturbations that break SO5 to some subgroup that are allowed by the UV symmetries. The UV system only has SO3 cross time reversal cross space group. So the leading such perturbation is this operator, right, which is Neel squared minus VBS squared. There's no symmetry rotating Neel to VBS. There's no SO5 symmetry. So this breaks SO5 to SO3 cross SO2. There are higher order terms that break it even further, but let's just focus on the leading term. And these are irrelevant at the CFT fixed point, but Once the system orders, it's going to determine whether the ordering is Neel or BBS. Right? So this is an example of what in condensed physics is called a dangerously irrelevant perturbation. Some of you might have heard that term. Now, what determines the sign of kappa? It's determined by the UV Hamiltonian, which I haven't specified. Right? So as I change parameters in an underlying lattice model, some models will have one sign of kappa, another models will have another sign of kappa. Right? So I can get any sign of kappa depending on the parameters of the UV model. So the RG flows will then look like this. If I turn off kappa, so I just have the continuum quantum field theory defined by the perturbations of the CFT. For either sign of lambda, I flow the SO5 broken phase. Now, if I turn on kappa, kappa is irrelevant to the CFT, but once I flow to the symmetry broken state, it's going to determine whether I get Neel or whether I get valence Bourne-Solf. Right? So if I'm living in this portion of the phase diagram of the low energy model, I have a phase transition between the Neel state and the Neel state itself. Right? And it goes through, as I cut across this axis, I flow, low energy physics will be controlled by the CFT, and it's a critical point that lives inside the Neel state.
Can you remind us which point has what global symmetry? So the origin is SO6.
Yes.
And along the x-axis,
Along the
Yes,
x-axis,
SO5.
it's SO5.
and it's spontaneously broken to SO4.
That's right.
And the others,
So the vertical axis, it has SO3 cross SO2 symmetry. And I should, in principle, I should have even more.
And merge into SO6, right?
No, the SO6 is already broken by this kappa. So
But it's irrelevant.
it's a, so the field theory here has SO3 to SO2. The fixed point has higher symmetry, which is SO6. I guess
That's what I'm saying.
yeah, I agree with that, of course. Yeah. Okay. So this is the story.
in the SO2, when did it start its life?
It started as a Z4 on the lattice.
But that's a lattice rotation.
It's a lattice rotation or lattice translation. It's a combination of the two. And that gets enlarged to SO2. And in principle, I should add symmetry breaking for that as well. If I'm in the Neel state, I can include it, but it doesn't affect the ground state. Here, I definitely should include it. It'll pick, it'll pin the orientation of this U1 order parameter to one of four possible choices. Right. So this critical point, does not separate two distinct phases of matter. Rather, it occurs within a single phase of matter. Right? And the single phase of matter is the most familiar phase in quantum magnetism. It's the Neel state. Right? And it could also occur in the BBS state. So in principle, so the phase diagram, let's just focus on the Neel state because that's what's seen in the experiments. We're living somewhere inside this region in experiments, right? So there's a line, if you tune one parameter, the surface of codimension 1 in coupling constant space, where you hit the CFT, right? But it's the same phase, and it should be possible to go around it smoothly and end up on, connect this point to this point.
But what do you mean go around it? Because,
How do I go around it?
but lambda's positive on one side and negative on the other side.
Oh,
So
that's in the
lambda equals 0, right?
No, that's in the continuum field theory. Right? In the original lattice model, there is no problem with going around it. I have any number of couplings that I can choose. Right? And it's the same phase. Anything that lives in the same phase, it's an infinite dimensional coupling constant space in UV. It doesn't have to come close to the CFT at all. I can be living here. I can go here, come back, and then come there. Right?
So there's lambda couples to O plus O dagger.
Yes.
And so on one side, that's positive, on the other side, that's negative.
But
So what is that operator in terms of the original spin model? O plus O dagger.
it has all the symmetries of the UV system. So any operator in the UV system will have some overlap. Any symmetric term, any term you put in the Hamiltonian that you're allowed to put in the Hamiltonian will have some overlap with this operator,
Yeah.
right? So S dot S, summed over the four bonds, S dot S plus S dot S plus S dot S plus S dot S plus S dot S. For instance, that will overlap this.
Is there something interesting that one can say about the endpoint of your green curve?
Yeah. So there is a different field theory that's a candidate for this. So you take this QED3 Lagrangian, and then you add a Gauss-Navier type interaction to a field that transforms in the vector representation of SO3. Right? So you introduce another field, right? Let me call it N. Right? N couples to a fermion bilinear with the same symmetries, and then there's a Gauss-Navier type transition. Right? So that's the natural candidate for this critical endpoint. Right?
And you're saying once you get to that, it just doesn't flow anywhere near the original fixed point
Exactly.
we're talking about. And then when you go past it, it just totally erases these distinctions that were there.
Exactly, yeah.
Where are the arrows on the green line? Where is the flow along the green line?
There's no flow.
There's no flow. This is a phase diagram, and
So
David will. Years back as a graduate student, I was given a hard time for drawing RG flows on phase diagrams. So I learned not to draw that ever again. Someone actually yelled at me for doing that.
What was that? Do you remember?
Leon Balkans.
Leon.
With good reason. But I was a very young, I'm still very young. But
Not compared to him, right?
Sorry, man. Yeah, no, not RG flow. Just saying that.
if you're at one of these points, and you just look at longer distances,
Yeah,
will you be at the same point? The point that you end, is it a multi-critical?
that's a multi-critical point.
And
That's
the
true.
green line, is it first or second order?
It's second order. The green line is what's controlled by the CFT that I've been talking about.
Right, and the green line, there's a multi-critical point.
Yeah, let's ignore the multi-critical point for now. Let's say I'm sitting here. This is controlled by this CFT,
Right,
right?
but if you started at the end point.
If I start at the end point, then there's
will
a
you go
different
in or
theory.
out? Will you go in and out? Will you go out along the green line or in?
Out or in, what is it?
There's a flow away from that point along the green line.
That's
So you're
right.
going out of.
So there's a relevant
So the
operator.
arrow, there is an arrow on the green line that
You
from
could-
the left to the
No,
right.
that's a decimal.
Yeah. If Balance isn't here, you can do that.
So there is a multi-critical point which has two relevant perturbations. One relevant perturbation is like that, let's say roughly like that. The other relevant perturbation is like this.
Okay, that answers my question.
All right, very good. Yeah.
Now we can balance can come in.
Sorry?
Now balance can come in.
No balance is coming. It's been, I mean, some side they go to the. But in any case, so this is an example of what we call an unnecessary quantum critical point. It's like a liquid gas transition where there's a sharp phase transition, but you can go around. Right? Here, the difference is that unlike in liquid gas, this is a continuous phase transition. Right? And there are many other examples of unnecessary quantum critical points in the last few years that we found. The first examples were in a context that's esoteric, both in condensed matter and in field theory. I was told by both field theorists and condensed matter theorists to stop doing such unnecessary work. So it was an SP and C gauge theories with NF fermions, with NF large enough, but both NC and NF was 0 more. But anyways, we found this example just fooling around. And it turns out there are some SPT to trivial transitions of fermions. There are some 1D models. So there's a folklore in condensed matter physics. Sometimes experimentalists will see evidence for quantum criticality in some experiment. Then there's a big question that everyone's talking about, which is, the big question is, what is the distinction between the phases on either side? Right? But once we know that this kind of example exists, it challenges the very premise of that question, right? A quantum critical point need not separate two distinct phases. It may just be a point in the phase, a line in the phase diagram of a single phase of matter, right? Anyway, so that's the story. So the summary is that we're still learning things about the Neel state on a square lattice. The world's best studied phase in quantum magnetism, and the phase that's routinely seen in experiments, hidden inside the Neel state, if you tune one parameter, I can't tell you which parameter in a lattice system to tune. This methodology doesn't give me that control. But I know that if you modulo the various assumptions that I've made, there's a non-trivial CFT that you can hit by tuning one parameter. And the CFT has a Lagrangian description as Dirac fermions with the U1 DHV. Right? And perhaps this is a useful thing to know because I motivated some of this by saying we want to see how you get a D-wave superconductor which has Dirac fermions, right? If the Neel antiferromagnet is close to this critical point, or maybe it gets closer to this, the spin physics becomes closer to this as you change the doping or something. Maybe you expose these Dirac fermions as the D-wave superconductor, as the Dirac node of the D-wave superconductor. The fact that this Dirac structure may be lurking inside the Neel state, perhaps that's a useful thing in the quest to understand this. And this phenomenon may actually be common, at least in theory, as a theoretical phenomenon, maybe not in experiments, in both condensed matter and field theory. We seem to be finding a growing number of examples. Let me stop.
So maybe that's a question. So I would like to understand the following thing. So in a P plus IP superconductor, you also have a transition from, there is a theoretical phase transition where you go from the P plus IP superconductor to the same, but there is a way of distinguishing the two phases.
Right.
By using a topological invariant.
That's right, yeah.
So is this different, or you could say that this is also?
No, this is different because here they're the same phase.
Well, there is also the same phase model.
No, they're distinct phases. One is end state, myelinoid states, the other doesn't.
Oh, that's it, but this is not the phase, it's something that you see on the boundary.
No, that's a bulk.
Characteristic.
That's a bulk characterization of the distinction between the strong pairing.
So then, okay, so that means that those do not qualify as something.
Those would not qualify. There are two distinct phases. They're not distinguished on the basis of the broken symmetry. They're distinguished on the basis of some other topological invariant in the bulk that captures the physics of the gap commutation.
So this line of critical points, one of them's in the, it's in the Neel phase and it's also in the BBS phase, but on the line of critical points, it's critical. You've lost the long range order of the BBS in the Neel phase.
That's it.
And they're both.
Yeah, so the Neel order parameter goes to 0 and then
kappa, which is broken, this, is biased you towards Neel or VBS is also irrelevant there, right?
Exactly, yeah.
But these two multi-critical points at the ends, they're probably different.
They're different.
They're different.
Yeah.
So that's a line of quantum spin liquids.
Yes, living inside either the Neel
It's a
or
line of quantum spin liquids.
it's a line of critical quantum spin liquids.
Yeah.
You just have to tune one parameter on the square lattice to
Yeah. And the point right at the boundary is special.
No, there's nothing special about it. So,
And equals.
so this transition is
No, the-
weakly first order. Right? This transition is weak first order.
But is it going to be first order on the green line?
No, it'll become continuous on the green.
Right, so then on the green line, doesn't it flow to the?
No, so there's a first order transition that becomes continuous and then becomes first order again.
Okay, you're saying that's not lambda equals 0,
That's not lambda equals 0. Lambda equals 0 is through this line. Yeah.
The whole green line is.
The whole green line is lambda.
Sorry.
Yeah, maybe Silvio and then.
The prospects for seeing this in numerical simulations.
Yeah, so there is a question that I don't know the answer to. Obviously, this level of analysis gives me no control, but I can ask the following question. Can this be accessed within a sign problem free model? Because then numerical simulations can go a long distance. So I don't know, the 3D3 Lagrangian can be simulated without a sign problem. Right? Now, whether that means that there is also a spin model in the same universality class that can be simulated without a sign problem, I don't know.
The Neel can be done without a sign
The
problem.
nail itself can, but maybe you're sitting somewhere here.
Yeah,
Right? So can you tune towards this without a sign problem? I don't know. But the fact that this theory itself is, there are some phases and some fixed points which are intrinsically have a sign problem. There is no formulation in which they are sign problem free. So for instance, chiral topological phases. So there are papers that show that they are like that. Like the red states, chiral edge states, you can't, there's no formulation for a sign problem. This is not like that. There is a sign problem free formulation of this theory, that just the QD3, the ground. But whether you can do it in the Hilbert space of spin half moments on lattice, which will enable you to do probably better simulation than lattice gauge theory simulation. I don't know.
If people put, additional terms in the Neel and they see Neel to VBS, then they see things that look a little bit like spin liquids.
I know. Yeah. So
So
they see this very weak first order transition, right? And they see this emergent SO5 symmetry. There's very good evidence for that.
right, as you go,
Here, as you cut
as
across.
you get close to the green line, it's got to become arbitrarily weak, right?
Exactly. So people also see.
Your phase diagram here automatically has weak, very weak first order phase.
I know. But I'm not confident enough to say that what people are seeing is because of proximity to this.
Yeah, right.
Right. That perhaps is not what's going on based on looking at the numerics for a long time, but the numerics may still change.
Yeah, no, these are hard.
Yeah, numerics is hard. But yeah,
So SO5 in the continuum is broken to SO4, right?
yeah.
Is it possible that the two, have you checked the two? So there is a SO4, and could it be that in two different sides there are two different SO4 SPT phases, or in the same SPT for SO?
Have I checked that? No, I haven't
But if
checked
you have
that.
free
So-
fermions, like there is a massless point for a free fermion is 1D, the
Yeah.
two sides are different SPT, like.
Yeah, so here's what I can say. So the sigma model description, if I go to the sigma model description and I freeze one of the 5 components of the SO5 vector, then the other 4 just are in a trivial state. Okay, that much I can guarantee. Okay, so yeah, I think there's no SPT associated with the remaining SPT.
I think in view of the time, we should postpone the
Right.
questions. So,